Today, we're going to demystify one of the most famous formulas in all of math. We're talking about the area of a circle. And trust me, getting to the why behind it is way more interesting than just memorizing the answer.
Area equals pi r squared. You've probably had that drilled into your head for years, but why that specific formula? Where does it actually come from? We're not just going to state the rule. Today, we're going to build it from the ground up.
So, to solve this puzzle, we first have to understand the main character in our story, that mysterious and amazing number, pi.
It all starts with a really cool concept called geometric similarity. It sounds kind of technical, but all it means is that two shapes are perfect scale models of each other. Same exact shape, just a different size. You know, like a big movie poster and a little postcard of that same poster.
Now here's a simple idea, but it's actually profound. All circles are similar to each other. Every single one. From the cap on a water bottle to a giant Ferris wheel. Every circle is just a scaled-up or scaled-down version of every other circle in the universe. And that similarity is exactly where pi comes from. See, because every circle is a perfect scale model, the ratio of how far it is around the edge, the circumference, to how far it is across the middle, the diameter, is always the exact same number. And that universal constant ratio is what we call pi. It's why a circle's circumference is always just pi times its diameter, or if you prefer, 2 pi r.
Okay, so we've got pi in our back pocket. Now we can finally tackle the area. And we're going to use this brilliant method. We're going to slice up the circle and rearrange the pieces into a shape we already know how to measure. It's pretty cool. So imagine slicing a circle like a pizza into a bunch of wedges. If you line those wedges up, alternating point up and point down, you get this kind of bumpy shape. But here's the trick. As you slice it into more and more thinner and thinner wedges, those bumpy, curved edges get straighter and straighter. The whole thing starts to look more and more like a parallelogram, which for our purposes is basically a rectangle.
So what are the dimensions of this new rectangular shape? Well, the height is easy. It's just the length of one of the pizza slices, which is the circle's radius, r. And the base? That's made up of the crusts from half of our wedges. Since the whole circumference is 2 pi r, half of that is just pi r.
And now for the moment of truth. We just have to find the area of our new parallelogram. That's just base times height. So that's pi r times r. And what does that give us? Pi r squared. And there it is. We didn't just memorize the formula, we actually just derived it by rearranging the pieces.
You know, this isn't just an abstract idea on a chalkboard. We can actually see it and touch it. These 3D printed models show how those wedges can be physically unrolled to form that exact same shape. It just makes the math feel so much more real and intuitive, doesn't it?
Now, what if I told you there's an even more elegant way to see this? A way that uses 2 circles instead of 1 and gives us an even cleaner result. This time, we're going to start with 2 identical circles, both sliced into wedges just like before. We've got our pink one and our gray one, all ready to go.
And here is where the magic happens. By taking the wedges from both circles and interlocking them, we smooth out those bumps almost completely. What we get is one beautiful, near-perfect rectangle. It's so clean.
So let's just quickly break down the math here. The height is still the radius, r. But now the base is made from the wedges of both circles. So that means it's one full circumference, or 2 pi r. The total area is 2 pi r times r, which gives us 2 pi r squared. But remember, that's the area for 2 circles. So we just divide by 2 to get the area of 1, and what do you know? We're right back at pi r squared. 2 different paths, same beautiful result.
But, you know, understanding the components of a circle isn't just about proving formulas. It unlocks a whole new way of seeing the shape. It actually lets us play.
As soon as you break that circle down into these real, tangible pieces, you are no longer limited by its original form. They literally become building blocks.
You can rearrange them into a spiky crown. Or you can unspool them into these elegant spirals. All of a sudden, math isn't just a rule on a page. It's a creative kit. The freedom to take things apart and put them back together, that's where deep understanding really comes from.
And all of this leads us to the biggest takeaway of all, a more powerful and frankly, more fun way to learn.
And this is the core idea right here. Formulas are important, absolutely, but they become truly meaningful when you can see where they come from and when you can build them yourself using different models, whether they're diagrams on paper or actual 3D objects you can hold.
So what should we take away from all this? First, that formulas aren't just rules to be memorized, they're discoveries waiting to be made. Second, using multiple models, seeing it, touching it, builds a much deeper understanding. And finally, that the very act of building, designing, and yes, playing is one of the most powerful learning tools we have.
And that leaves us with one last question. We took one of the most famous formulas in math, and we came to understand it, not by memorizing, but by taking it apart and putting it back together. It really makes you wonder, what else, in math or just in life, could we truly understand if we just decided to play with it?